Will the history of astronomy be divided between before Webb and after Webb?
Yes, I believe it will be.
Of this telescope, of this remarkable instrument we put in space, is finding things that we didn't expect.
For centuries, humanity has gazed at the night sky, seeking answers to the origins of the universe. But with the launch of the James Webb Space Telescope, our understanding of the cosmos is undergoing a seismic shift, one so profound that the history of astronomy may soon be divided into before Webb and after Webb. As its infrared eyes pierce deeper into space than ever before, Webb is unraveling mysteries that challenge the very foundation of cosmology. For instance, just recently, the James Webb Telescope saw the first object beyond the Dark Ages, but what it found stunned everyone. Hold tight, because this is going to be a wild ride. Let's get started. The discovery that shook cosmology. For decades, astronomers have theorized about the earliest epochs of the universe, struggling to piece together how the first galaxies formed in the wake of the Big Bang.
Rendell was born nearly 900 million years after the Big Bang event at the outset of the universe. But
in a discovery that has sent shockwaves through the field of cosmology, the James Webb Space Telescope has detected an enigmatic cosmic structure, a luminous, well-formed system existing at a time when the universe was barely 400 million years old. This extraordinary finding challenges long-standing models of galaxy formation, offering new insights into the nature of the early universe, while simultaneously solving a persistent astronomical puzzle: the unexplained presence of bright, massive structures in an era previously thought to be dominated by diffuse hydrogen gas and the slow emergence of primordial stars. This may not seem like much. After all, we've been finding new cosmic phenomena pretty much every single year since the launch of the Hubble and then the JWST. But this is big, huge. The newly discovered structure, detected through JWST's unparalleled infrared vision, appears to be a compact yet surprisingly bright assembly of matter. In other words, it is far more evolved than expected for such an early epoch. According to conventional models, the first galaxies were thought to be relatively dim, amorphous clouds of gas that took hundreds of millions of years to coalesce into recognizable formations. Yet, JWST has captured something strikingly different.
Webb now has its array out, confirmation that it is power positive.
A luminous structure radiating intensely in the deep infrared, suggesting that fully formed stars and complex interactions were already underway at a time when the universe was less than 3% of its current age. What makes this discovery particularly staggering is the sheer brightness of the structure. In theory, the first galaxies should have been small and faint, gradually accumulating matter through slow accretion processes. However, the detected system emits light comparable to galaxies seen much later in cosmic history. But wait, let's get some perspective first to better understand this anomaly. The Dark Ages of the universe. For nearly 100 million years after the Big Bang, the universe lay shrouded in an opaque darkness, an era so impenetrable that even the most powerful telescopes ever built could not glimpse what lay beyond. This period, known as the Cosmic Dark Ages, was a time before the first stars ignited, before galaxies took shape, and before light as we know it existed. Space was filled with a thick, featureless fog of primordial hydrogen and helium, stretched thin by the universe's relentless expansion, but not yet dense enough to coalesce into luminous structures. These Dark Ages began roughly 380,000 years after the Big Bang, following a momentous event called recombination. Before this point, the universe was a dense, hot plasma of charged particles, constantly scattering photons and preventing light from traveling freely. But as the universe cooled, protons and electrons combined to form neutral hydrogen, allowing light from the Big Bang, now observed as the cosmic microwave background, to spread across the cosmos. However, this newly transparent universe was not yet bright. It was vast, cold and featureless, without a single star to illuminate it. For millions of years, gravity worked in near silence, drawing together tiny density fluctuations in the primordial gas. These regions of slightly higher mass would eventually grow into the first stars and galaxies, but this process was slow, stretching across tens of millions of years. During this time, the universe was effectively dark, with no visible or infrared light being produced. Scientists long believed that this phase was beyond our observational reach.
Trying to get them ready for when they're revealed to the world. I think that's just an important moment, because it's not just an important feat for science.
When peer deep into space, we're actually looking back in time. But how far back in time we can look has always been a limiting factor. For instance, traditional telescopes, including the Hubble Space Telescope.
We're seeing bulb blankets unfurl on the solar array.
Rely on detecting visible and ultraviolet light, but these wavelengths simply did not exist during the Dark Ages. Without stars, there were no sources emitting such radiation, leaving astronomers with no way to probe this era directly. Even radio telescopes, which detect long wavelength emissions, faced challenges because the neutral hydrogen gas that filled the universe absorbed most radiation. All of this meant that it was nearly impossible to observe what was happening within these vast, unlit clouds. Another challenge was redshift, which is the stretching of light as the universe expands. Any radiation emitted from this period would be stretched far into the infrared by the time it reached us, making it effectively invisible to traditional telescopes.
Team inside the Webb Space Telescope's flight control room.
Scientists could study the aftermath of the Dark Ages, the period of reionization when the first stars began breaking apart this cosmic fog, but they had no way of seeing the earliest stages of cosmic evolution. That is until JWST entered the picture. Against all expectations, JWST has now detected faint signatures of light originating from these primordial clouds. While no stars had yet formed, astronomers theorized that weak energy emissions could have emerged from either the collisional excitation of hydrogen or primordial black hole activity. In the first case, the vast clouds of neutral hydrogen may have been disturbed by gravitational interactions or early density waves, causing atoms to collide and emit weak infrared radiation.
That infrared information is giving us so much more details that we could get with the Hubble in the visible.
JWST's sensitivity to infrared light allowed it to detect these subtle emissions. Another intriguing possibility is that microscopic black holes, formed in the chaotic aftermath of the Big Bang, could have begun accreting matter far earlier than expected. As matter spiraled into these black holes, it may have released faint bursts of energy, providing the first flickers of light in the darkness. The mere fact that JWST has been able to detect anything from this period is revolutionary. These findings not only offer a rare glimpse into a previously hidden chapter of cosmic history, but also challenge the traditional view that the universe was completely dark before the first stars formed. If weak emissions were already present during the Dark Ages, it suggests that the transition to the first luminous structures was far more complex and gradual than previously believed. This discovery is just the beginning. By probing deeper into the Dark Ages, JWST may uncover more about the conditions that led to the birth of the first stars and galaxies. Were there other unknown sources of early radiation? Could exotic physics, such as decaying dark matter, be responsible for these unexpected emissions? For now, all we can say is that the cosmic Dark Ages were not as we thought they were. Let's try and understand, though, why we saw what we did, especially considering that scientists predicted that we couldn't. The unexplained light in the Dark Ages. One of the greatest cosmic mysteries came to light back in the mid-20th century, when early infrared and radio observations picked up a faint, persistent glow coming from deep space. Unlike the well-studied cosmic microwave background, which is the afterglow of the Big Bang itself, this light did not match any known radiation sources. It wasn't coming from galaxies, quasars, or nebulae. Rather, it appeared as a diffuse, all-encompassing emission stretching across vast regions of the cosmos. This was particularly baffling because it seemed to originate from a time before the first stars formed, an era when the universe was expected to be completely dark. Astronomers initially assumed the signal might be an observational artifact or stray light from known cosmic structures. However, As instruments became more refined, the signal persisted. The European Space Agency's Infrared Space Observatory and later NASA's Spitzer Space Telescope confirmed the anomaly, but neither could pinpoint its source. The discovery of the extragalactic background light,
the light from the most distant galaxies, has taken billions of years to travel across the universe,
and the cosmic infrared background added more complexity, as these diffuse emissions contained components that did not match expected contributions from galaxies alone. Some regions of the sky exhibited an excess glow, leading to speculation that something else, something unseen, was illuminating the ancient universe. Over the years, numerous hypotheses emerged to explain this puzzling glow. One theory proposed that the early universe contained massive clouds of primordial gas that collapsed into compact, star-like structures, but never fully ignited. These objects, known as dark stars, or population 3 remnants, could have emitted faint radiation through gravitational heating or exotic particle interactions. Some physicists speculated that this unexplained light
do this measurement and see if they come up with the same answer.
Instead, we found something even greater, which was a surprise that the universe wasn't starting.
Might be the result of dark matter particles decaying or annihilating in deep space. Certain theoretical models predicted that dark matter, which is invisible by nature, could produce faint electromagnetic emissions under specific conditions. If true, this would be the first indirect detection of dark matter. Another intriguing possibility was that primordial black holes, formed shortly after the Big Bang, could have slowly accreted gas, producing weak but persistent emissions long before the first stars were born. Unlike supermassive black holes in modern galaxies, these early black holes would have been much smaller and scattered throughout the cosmos, generating diffuse radiation. Some astronomers believed that small, dense clumps of gas, precursors to the first galaxies, could have emitted weak Lyman-alpha radiation due to early ionization effects. This could mean that the cosmic dark ages were not as dark as once thought, and that light-producing interactions occurred earlier than expected. Despite these theories, direct observational proof remained elusive. The light was there, but its source was unknown. But the JWST finally brought new clarity to this long-standing enigma. JWST's findings suggest that the mysterious glow may be the result of gravitationally heated primordial gas clouds, dense regions of hydrogen and helium collapsing under their own gravity, emitting weak radiation long before the first stars formed. Unlike conventional star formation, these clouds did not generate fusion reactions, but instead released energy through molecular cooling and turbulence, producing a diffuse glow that filled the early universe. This explains why the signal appeared as an all-encompassing background rather than localized sources. Additionally, JWST has provided indirect evidence supporting the theory of early black hole formation. Some of the light may be linked to small-scale accretion activity in primordial black holes, confirming that these enigmatic objects existed far earlier than once assumed. If true, this would reshape theories about black hole evolution, suggesting that they played a crucial role in shaping the cosmos before galaxies took form. However, now one can't help but wonder about a bunch of other stuff. Let's throw some more light on these other mysteries, ancient galaxies that should not exist. When the JWST first peered deep into the early universe,
the universe as it's never been seen before. Here's Stu Benitez.
It uncovered two ancient galaxies that, by all known cosmological models, should not exist. These galaxies, among the most distant ever observed, date back to a time when the universe was less than 400 million years old. Yet, unlike the chaotic, irregular galaxies expected in such a young cosmic era, these structures were surprisingly massive, well-formed, and mature. Labeled as Glass Z12 and Sears 1749, these galaxies were formed within the first few 100 million years after the Big Bang. Given the widely accepted lambda cold dark matter model of cosmology, galaxies at this stage should be small, clumpy, and just beginning to assemble their first stars. Instead, these galaxies were unexpectedly massive, with mature structures and well-organized features, more reminiscent of galaxies billions of years older. To put this into perspective, the galaxies appeared to contain tens to hundreds of billions of stars, something that should have taken over 1 billion years to achieve. This directly contradicts the theoretical timeline of structure formation, which suggests that early galaxies should have been dim, irregular clusters of newly forming stars, not fully developed cosmic giants. The discovery was not just surprising, it was outright disturbing to astrophysicists who believed they had a solid understanding of how galaxies evolved. The standard cosmological model suggests that galaxies grew gradually over hundreds of millions of years, forming through the slow accumulation of gas and the mergers of smaller structures. However, these newly discovered galaxies appear to have skipped this gradual process entirely. Unlike the chaotic, irregular shapes expected in primordial galaxies,
and the brightest image there is about the same brightness as Pascal's galaxy there.
These ancient structures appear more defined and structured than anticipated. Moreover, the presence of heavy elements in these galaxies is another mystery. Elements heavier than hydrogen and helium are produced in the cores of massive stars and spread through supernova explosions. For such elements to be abundant in these galaxies, multiple generations of stars would have needed to live and die within just a few 100 million years. This rate of evolution is far beyond what our models predict. The implications of these findings are profound. If these galaxies truly exist as observed, there are only a few possible explanations, each of which would require a significant revision of modern cosmology. One possibility is that our understanding of cosmic expansion is incomplete, and the early universe evolved far more rapidly than we thought. Another explanation is that star formation in the early universe was far more efficient than expected. The most radical implication is that our entire model of galaxy formation needs revision. If galaxies can form much earlier and more rapidly than our simulations suggest, it could mean that our understanding of dark matter, gravity, and the very structure of the universe needs to be re-evaluated. Some physicists have even speculated whether modifications to fundamental theories, such as tweaks to the laws of gravity or the inclusion of new physics beyond the standard model, might be necessary to explain JWST's findings. If you thought our confusion ends here, you'd be wrong. There's more. Lyman-alpha emission and galactic mergers. Lyman-alpha emissions are produced when hot young stars ionize surrounding hydrogen gas, causing it to glow in a distinct ultraviolet wavelength. This signal can reveal key details about a galaxy's age, composition, and rate of star formation. In the modern universe, Lyman-alpha emissions are relatively easy to detect. However, in the early cosmos, particularly during the epoch known as cosmic reionization, approximately 400 million to 1 billion years after the Big Bang, this light should have been almost completely absorbed by thick clouds of neutral hydrogen that filled the universe. But guess what? The JWST has detected these emissions from some of the most ancient galaxies ever observed. So, what does this mean? One possible explanation for the unexpectedly strong Lyman-alpha emissions is that these early galaxies were undergoing violent and frequent mergers. During a galactic merger, intense gravitational interactions compress gas clouds, triggering rapid bursts of star formation. This extreme starburst activity produces vast amounts of ionizing radiation, which in turn excites the surrounding hydrogen gas, leading to strong Lyman-alpha emissions. JWST has revealed that early galaxies were far more dynamic than previously thought. Instead of evolving gradually, many appear to have grown explosively through mergers, pulling in smaller galaxies and accumulating mass at astonishing rates. These collisions may have played a key role in creating the conditions necessary for Lyman-alpha light to escape. While galactic mergers and star formation explain the production of Lyman-alpha emissions, they do not fully explain how this light escaped detection when it should have been blocked by the neutral hydrogen filling the young universe. The intergalactic medium was mostly opaque to ultraviolet radiation, meaning that even if early galaxies emitted Lyman-alpha photons, they should have been absorbed before reaching telescopes like JWST. However, the new data suggests that something was allowing these signals to travel freely through space. For starters, instead of the rionization of the universe happening in a uniform, large-scale process, it may have occurred in patchy, localized regions around the first galaxies. This means that powerful starbursts and mergers may have carved out ionized bubbles in the surrounding neutral hydrogen, allowing Lyman-alpha photons to escape more easily. Another possibility is that some regions of the early universe contained less neutral hydrogen than predicted, meaning that the absorption of Lyman-alpha light was weaker than expected. If this were true, it would indicate that cosmic rationalization began earlier or more rapidly than previously assumed. Some scientists speculate that these findings could point to unknown physical processes influencing light propagation in the early universe. If Lyman-alpha photons are escaping from environments where they should have been absorbed, it may suggest that we do not fully understand the interaction between early galaxies and the surrounding intergalactic medium. Moreover, if galaxies were already forming ionized regions around them much earlier than expected, then it means that the timeline of ionization needs revision. Instead of occurring gradually over hundreds of millions of years, it may have happened more rapidly in localized, high-energy pockets, driven by extreme starburst activity. Additionally, these findings suggest that early galaxies may have been far more active and chaotic than previously believed. Rather than slowly assembling into large, structured formations, they appear to have been colliding, merging, and triggering intense bursts of star formation at a pace that defies conventional models. Astronomers are now searching for additional high-redshift galaxies, displaying strong Lyman-alpha emissions to determine whether this phenomenon is widespread. If JWST continues to find such galaxies, it will provide critical insights into how and when the first luminous structures in the universe emerged. Wait though, there are more oddities to follow. The presence of massive black holes. The JWST also spotted a supermassive black hole lurking at the heart of a galaxy that existed less than 500 million years after the Big Bang. Again, according to our current understanding of black hole formation, such an enormous object simply should not exist at such an early stage in the universe's history. Black holes are thought to grow gradually over hundreds of millions or even billions of years, either by accreting surrounding matter or merging with other black holes. Yet, this cosmic behemoth appears to have formed too quickly, too early, and at a scale that defies conventional models. The black hole in question is not just massive, it is supermassive, likely containing over 1 billion times the mass of the Sun. In the modern universe, such black holes are found at the centers of giant galaxies like the Milky Way, but they form over eons through gradual accretion and mergers. Finding one so soon after the Big Bang contradicts these timelines and suggests that black holes in the early universe must have formed through an entirely different process. Current models propose that black holes begin as the remnants of massive stars, stellar mass black holes, only a few times the mass of the Sun, and grow over time. However, this newly discovered supermassive black hole would have had less than 500 million years to form, which is nowhere near enough time for a stellar mass black hole to grow to such an extreme size. This raises the urgent question: did black holes in the early universe form through an unknown mechanism? To explain this paradox, astrophysicists are considering several radical possibilities. One of the most intriguing possibilities is that early black holes formed through a process known as direct collapse, rather than the slow accumulation of matter over time. In this scenario, vast clouds of primordial gas collapsed directly into black holes without first forming stars. Unlike typical black hole formation,
black holes are among the most fascinating objects in our universe,
which begins with a supernova explosion. Direct collapse, black holes could start their existence at tens or even hundreds of thousands of solar masses, allowing them to rapidly grow into supermassive black holes. If direct collapse black holes were common in the early universe, it would fundamentally alter our understanding of cosmic structure formation. Instead of stars forming first and later creating black holes, some regions of the early universe may have skipped the stellar phase entirely, leading to the creation of enormous black holes that shaped the first galaxies. Another possibility is that early black holes grew far more efficiently than expected, devouring matter at rates that exceed current theoretical limits. The Eddington limit, a fundamental principle in astrophysics, states that a black hole can only accrete material at a certain maximum rate before the outward pressure of radiation prevents further growth. If this limit was somehow exceeded in the early universe, it could explain how black holes grew to supermassive sizes so quickly. One possible way for this to happen is through super-Eddington accretion, where dense gas flows directly into a black hole at speeds and densities that allow for explosive growth. If early black holes could sustain this kind of extreme feeding frenzy, they may have ballooned to enormous sizes in a fraction of the time expected. However, this challenges one of the most well-established principles of astrophysics, and would require an unknown mechanism allowing black holes to grow far more efficiently than they do today. A more speculative but equally fascinating possibility is that some black holes were born directly from the Big Bang itself. These are known as primordial black holes, hypothetical objects that could have formed from extreme density fluctuations in the very first moments of the universe. If such black holes existed, they could have started out far more massive than stellar mass black holes, allowing them to reach supermassive sizes at astonishing speeds. Primordial black holes would revolutionize our understanding of the early cosmos, dark matter, and even the fundamental laws of physics. If they were common, they could explain a range of unsolved mysteries, including the unexpectedly high number of massive black holes detected by JWST. However, there is currently no direct evidence that primordial black holes exist. In the coming years, JWST will analyze more of these early galaxies to determine how widespread these massive black holes were. Astronomers will also use upcoming telescopes, such as the Nancy Grace Roman Space Telescope and the Extremely Large Telescope, to gather even more precise data about black hole formation in the first few 100 million years of the universe. For now, the existence of a supermassive black hole so soon after the Big Bang is forcing scientists to rethink the very foundations of how galaxies and black holes form. Whether this leads to a refinement of current models or a revolutionary new understanding of the cosmos, one thing is certain: the universe is far more mysterious and complex than we ever imagined. Speaking of mysteries, we have more of them. Is our understanding of cosmology wrong? For decades, cosmology has been guided by a well-structured timeline. The Big Bang, the Dark Ages, the formation of the first stars, and then the emergence of galaxies hundreds of millions of years later. However, the James Webb Space Telescope has thrown this timeline into disarray by uncovering massive, well-formed galaxies that existed far earlier than previously thought possible. These discoveries have ignited a heated debate among astrophysicists, with some questioning whether our understanding of galaxy formation, cosmic evolution, and even the age of the universe itself is fundamentally flawed. Could it be that the universe is older than 13.8 billion years? Or did something extraordinary and unknown happen shortly after the Big Bang that allowed galaxies to form at unprecedented speeds? If JWST's findings continue to hold, our entire framework for how the cosmos unfolded after the Big Bang may need a radical revision. According to the standard model of cosmology, the first galaxies should have taken several 100 million years to form after the Big Bang. The early universe was a hot, dense plasma that had to cool, allowing atoms to form during recombination, which led to the Dark Ages, a time before the first stars ignited. After a few 100 million years, the earliest galaxies were expected to appear, gradually assembling through gravitational attraction. But JWST has detected massive, well-formed galaxies at redshifts of 12 to 16, corresponding to a time just 200 to 300 million years after the Big Bang, far earlier than standard models predicted. these galaxies shouldn't exist because there wasn't supposed to be enough time for gas and dust to clump together under gravity and form stars. Moreover, the early universe was still filled with neutral hydrogen, which should have suppressed early galaxy formation. And most notably, the rate of star formation required to produce such massive galaxies exceeds what physics currently allows. Some astrophysicists suggest that galaxies formed much more efficiently than previously thought, but this alone doesn't fully explain the data. The issue is not just that galaxies formed early, but that they appear far too mature, bright, and massive for their age. If these galaxies are indeed as old as they appear, this has forced us to rethink how galaxies form. Also, we must consider the possibility that the universe is older than we thought, or maybe something unknown accelerated the formation of galaxies after the Big Bang. Whatever it is radically different from what we know. The age of the universe is based on measurements of cosmic expansion using the Hubble constant and observations of the cosmic microwave background. These calculations suggest the universe is 13.8 billion years old, but JWST's discoveries are making some scientists reconsider this number. If galaxies were already forming less than 250 million years after the Big Bang, it suggests that either the expansion rate of the universe has been miscalculated, or the universe itself is older than we currently estimate. While increasing the universe's age by a few hundred million years might not seem drastic, it would reshape our entire understanding of cosmic history. But there are other possibilities as well. Maybe the Hubble constant has been miscalculated, meaning the universe could be a billion years older than previously thought. Or maybe there was an unknown era of accelerated cosmic evolution that condensed the formation of galaxies into a much shorter time span. We must also be open to the possibility that the standard Big Bang model may be incomplete. While these ideas are still controversial, JWST's findings have reopened debates about the accuracy of our cosmic clock. A more radical idea is that our model of the Big Bang itself is incomplete. Some physicists propose that the universe may have undergone a period of pre-Big Bang existence, where structures had already started forming in a previous cycle of the universe. The concept of a cyclic universe, where the cosmos undergoes repeated phases of expansion and contraction, has been explored in various theories, including loop quantum cosmology. Whatever the case, the James Webb Space Telescope has pushed the boundaries of observational astronomy, delivering discoveries that challenge the very foundations of modern cosmology. With its unparalleled ability to peer into the depths of cosmic history, it has revealed galaxies that seem too mature, too massive, and too structured for their place in the early universe. But while these findings have sent shockwaves through the scientific community, they remain at a crucial crossroads, awaiting spectroscopic confirmation of their redshifts. If these redshifts hold true, meaning that these galaxies genuinely existed within the first few hundred million years after the Big Bang, cosmology as we know it may require a dramatic overhaul, revision, or even a complete rewriting. Future telescopes, such as the upcoming Nancy Grace Roman Space Telescope and next-generation ground-based observatories, will provide additional data to either support or refute JWST's most astonishing findings. Until then, the scientific world waits with bated breath, knowing that the next few years could redefine our understanding of the universe in ways we never imagined. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.